Now that we've had a good understanding and a good run through of all the quantum numbers, let's look at a few examples in this video. This video picks up with example 11, which is asking for what is the maximum number of, and then has some stipulations. So let's take a look at each situation and figure out what the maximum number of whatever they're looking at would be. First one, what would be the maximum number of electrons that are allowed in the 2px orbital? Now, you might be thinking, what the heck does that mean? Well, just so you know, the 2 indicates what energy level it's on. The p obviously indicates what shape we're looking at. And the sub x indicates it's along the x-axis, meaning it's talking about that specific orientation of the p orbital. But regardless, notice it's saying, what is the maximum number of electrons allowed in the blah, blah, blah orbital? It doesn't matter what it says. How many electrons are allowed maximum? 2. It does not matter what orbital we're looking at. All right. Let's look at the second question here. What is the maximum number of subshells that are allowed in the fourth shell? So when it says fourth shell, we're saying n equals 4. So what is the maximum number of subshells? Meaning, what's the maximum number of shapes that we're looking at? Well, if we're looking at n equals 4, the maximum value for L is 3. But that also includes L equals 0, L equals 1, and L equals 2. So it looks like the number of subshells or shapes is 4. So there are 4 subshells maximum allowed in the fourth shell. Be careful on that one, by the way. If it had said, what's the maximum value of L in the fourth shell, then you would say 3. But number of subshells, there's actually 4. All right. What is the maximum number of electrons allowed in the 3D subshell? Remember, the 3 is just indicating what level it's on, or what shell or distance. But it's a D subshell. Remember how many electrons a D subshell can hold? It's 10. What about maximum electrons allowed in the 4D subshell? Still going to be 10. Doesn't matter that it's in a different energy level. What about maximum number of electrons allowed in the 3P subshell? Well, a P subshell, even doesn't matter what energy level, can hold 6. What's the maximum number of electrons allowed in the third shell altogether? So, okay, if we're looking at n equals 3, the entire third shell, well, that means the maximum value for L is 2, but you also have L equals 1 and L equals 0, meaning you have an S, a P, and a D subshell. The S can hold 2, the P can hold 6, the D can hold 10. So maximum altogether, the third shell altogether can hold 18 electrons. And finally, what's the maximum number of orbitals in the third shell? So we just figured out in the third shell, you have 18 electrons. But if 18 electrons need to be dispersed in orbitals, how many orbitals would you need to hold those 18 electrons? Every orbital can hold 2. So 2 electrons per orbital. That means there are 9 orbitals that would be allowed in the third shell. Another way to think about that, if that didn't make sense to you, is, let me erase this for a second. If your L values are given here as 0, 1, and 2, then our M sub L values could be figured out. Remember, M sub L is negative L to positive L. So if L equals 0, the only value for M sub L is 0. For L equals 1, it's negative 1, 0, and positive 1. And for L equals 2, it's negative 2, negative 1, 0, positive 1, and positive 2. Every single one of those numbers is an orbital. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's another way you could have solved that problem. Example 12. What is the maximum number of electrons in an atom that can have the following quantum numbers? So each of these letters, A through D, is a separate question. So let's take a look at the first question, A. What it's saying is how many electrons in an atom could have an n value of 3, and that's it, right? N value of 3. Well, I'm not going to go through it again. We did it back here. Remember how we figured out that when n equals 3, how many electrons were in the third energy level? 18. All 18 of these electrons, every single one of them will all have one thing in common, and that's their n value. They'll all have an n value of equal to 3. So to answer this question, what's the maximum number of electrons that can have an n value of 3 and that's it? 18. Okay, let's get a little bit more specific. What's the maximum number of electrons that can not only have an n value of 3, but additionally will also have an L value of 2? So if we go back, well, in the third energy level, when we got down to here, L equals 2, what did that mean? That means that we're looking at the D subshell. And we said that the D subshell can hold 10 electrons. So those 10 electrons will all have the same N value and the same L value. And so 10 electrons is the maximum number of electrons that can have both of these in common. Let's get a little bit more specific. Let's look at this set of quantum numbers. How many electrons would all have these three quantum numbers in common? So we're looking at the fourth energy level, specifically the L equals 2 value, which by the way is the D subshell, but specifically the M sub L value of equal to 0. Remember, what happens when you get down to the M sub L value? What is that telling you? That's an orbital. You have now gotten down to the specific orbital. How many electrons maximum can be in an orbital? 2. And finally, how many electrons in an atom could have all 4 of these quantum numbers in common? Just 1. Only 1 electron can have this exact set of 4 quantum numbers. No 2 electrons can have the exact same 4 sets of quantum numbers, because that would actually violate what we call the Pauli exclusion principle. We'll learn about this later, but it's a good idea to bring it up now. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. That's like you and I having the same address. I don't think we have the same address. I'll have to check the rooms to make sure you're not living here. That's creepy, right? We could have the same city. We could share the same city, state, zip code. We could even share the same street, but we can't share the same house number with all of that, right? It's the same for electrons. Example 13. Last example here. Which of the following sets of quantum numbers are allowed for an electron in an orbital of an atom? Select all that apply. So I've given you 4 sets of quantum numbers. Remember, every electron has its own 4 sets of quantum numbers. So we're just going through and seeing which ones are allowed, okay, which ones are valid. So here's how I solve this one. What I do is I look at my N values. We have N equals 1, 3, 4, and 2. Okay. Reminder that when you know the N value, you can then know what the allowed values are for L. And once you know the L value, you can then know the allowed values for M sub L. They kind of build on each other. So first thing I'm going to look at is I'm going to compare the L value, or the N value, to the L value. If N equals 1, can L equals 1? No. That's not allowed. If N equals 3, can L equal 0? Yeah. Because the maximum value for L would be 2. So it could be 0, 1, or 2. So that's allowed. So B so far is a good contender. If N equals 4, could L equal 1? Absolutely. Because if N equals 4, the maximum value for L is 3. So that's a contender. And then if N equals 2, can L equals 1? Yes. And so far, we have B, C, and D that are contenders. Now what I have to do is I have to look at the L value, and based on that, is the M sub L value provided allowed? So let's go back to B, since I've already figured out A is not possible. If L equals 0, can M sub L equal 0? Yes. In fact, that's the only value M sub L could be. So B is allowed. Looking at letter C, if L equals 1, can M sub L equal negative 1? Absolutely. Because the L equals 1 means it could be negative 1, 0, or positive 1. So letter C is allowed. Finally, letter D, if L equals 1, can M sub L equal 2? No, that's not allowed. So B and C are possible sets of quantum numbers. That wraps up section 5 for quantum numbers. We'll see you in section 6 when we talk about electron configurations.